In 2015, scientists detected something extraordinary. Two black holes colliding 1.3 billion light-years away, releasing more energy in a fraction of a second than all the stars in the universe combined. Since then, they've detected over 200 more. And what they're learning from these cosmic collisions reveals exactly what will happen when Sagittarius A star, the black hole at the heart of our galaxy, meets its match. This is episode 3 of the Space Vault's Black Hole Chronicles. Today, we're witnessing the ultimate cosmic showdown. The Andromeda galaxy is racing toward us at 250,000 miles per hour. In 4.5 billion years, it will collide with the Milky Way in the most spectacular event our local universe will ever see. But here's what makes this fascinating. We don't have to wait to understand what happens. We're learning the physics of black hole mergers right now, from collisions happening across the universe. Let me show you what scientists discovered. On September 14, 2015 at 5:51 a.m. Eastern Time, two detectors in Louisiana and Washington simultaneously recorded a signal that had traveled for 1.3 billion years to reach Earth. It lasted less than a second. A faint chirp in the data. But that chirp changed everything. For the first time in human history, we had directly detected gravitational waves, ripples in the fabric of spacetime itself, from two black holes merging into one. Now, the black holes LIGO detected were relatively small, stellar mass black holes formed from dying stars, weighing 29 and 36 times the mass of our Sun. But the physics is the same whether you're talking about stellar mass or supermassive black holes. The gravitational waves, the death spiral, the final merger, it all works the same way, just on a much, much larger scale when supermassive black holes collide. So what did LIGO teach us about how black holes merge? When two black holes orbit each other, they create gravitational waves that ripple outward through space-time at the speed of light. And every wave they emit drains energy from their orbit, pulling them closer together. Think of it like this. Imagine spinning two massive weights on strings above your head. As they orbit, they create waves in the air around them. But creating those waves requires energy, and that energy has to come from somewhere. It comes from the motion of the weights themselves. Each wave they create slows them down slightly. Black holes work the same way. For millions of years with supermassive black holes, this happens slowly. They might be light years apart, orbiting once every few thousand years. But here's where it gets wild. The closer they get, the faster they lose energy. It's an exponential process. When they're light months apart, they orbit faster, creating stronger waves, losing energy faster, spiraling inward faster. The process accelerates. That chirp LIGO detected? That was the sound of the final moments, when the black holes were so close that space-time itself was screaming, warping and twisting, as these objects completed their final orbits in a fraction of a second. In the LIGO detection, the entire merger, from the moment the signal became detectable to the final collision, took just 0.2 seconds. In that fifth of a second, the black holes released more energy than all the stars in the observable universe combined. That's the power we're talking about. Now scale that up to supermassive black holes. When Sagittarius A star merges with Andromeda's 100 million solar mass giant, the physics will be identical, but the scale will be millions of times larger. The gravitational waves will be so powerful that if humanity's technology survives that long, we could measure them from Earth. But what emerges from this collision? A single monstrous black hole, potentially 100 million solar masses or more, sitting at the heart of a new galaxy astronomers have nicknamed Andromeda. But here's what surprised scientists. The new galaxy looks nothing like what we have today. Instead of the elegant spiral arms of the Milky Way, Andromeda will be an elliptical galaxy, a vast, football-shaped swarm of stars with no defined structure. The orderly rotation we're used to, gone. Replaced by chaotic stellar orbits, creating a completely alien cosmic environment. Now you might be wondering, what happens to Earth? The distances between stars are so vast that direct collisions are incredibly rare. If our Sun were a golf ball, the nearest star would be 1,000 miles away. Even in a galactic collision, the odds of two stars hitting each other are astronomically small. Our sun might end up in a completely different part of Andromeda, with an alien night sky full of unfamiliar constellations. But the planets? They'll likely remain in their orbits, oblivious to the cosmic chaos around them. The new supermassive black hole will continue the work Sagittarius A star started, regulating star formation, heating and cooling the galactic environment, shaping the evolution of billions of stars for billions of years to come. From its violent birth 9 billion years ago, to its discovery by Nobel Prize-winning astronomers, to its inevitable merger with Andromeda's black hole. This is the epic story of the invisible force that controls our galaxy. But the universe is full of these cosmic titans. Since 2015, we've detected over 200 black hole mergers through gravitational waves. Each one teaches us more about the most violent events in the universe. And we're only beginning to understand them. What other mysteries are waiting to be discovered? What cosmic collisions are playing out in galaxies we haven't even observed yet? Thank you for joining me on this journey through the Space Vault's Black Hole Chronicles.